Hello, welcome to lecture 15 of the course. This is lecture number 5 of the module 2. In the last lecture, we learned how to quantize a transmission line and a transmission line resonator. In this lecture, we will see how this quantization leads to the so-called Jaynes Cummings model, and we are going to discuss this model in somewhat great details in this class. So let us begin.
Have a quick recap of what we have done in the last class. In the last class, we quantized the infinite transmission line, taking the magnetic flux as the coordinate, and it turns out that charge would be momentum, and the Lagrangian of this transmission line, discrete transmission line, we wrote as the difference between the electrical energy and the magnetic energy, and we got from this Lagrangian that indeed the momentum is nothing but the charge. And you should recall that this magnetic flux is related to the voltage in the transmission line by this expression, and from here you see that the charge at a particular branch and at a particular node we can get it just by taking the time derivative of the flux and then multiply it by the capacitance. And again the current can be found just by taking the difference in the magnetic flux value at two neighboring nodes, and that is going to give you the current that is driven in that particular branch. And then use in terms of this magnetic flux, we can write down this Lagrangian, and from here we immediately get our Hamiltonian. This is the classical Hamiltonian, and it turns out that this momentum and the coordinate, they are canonically conjugate variables, so therefore we can invoke the canonical quantization method, and we do that by writing the variable magnetic flux in terms of operator and the momentum in terms of the momentum operator, and invoking this Heisenberg-Uncertainty relation, we can quantize it. And so the quantized Hamiltonian for the transmission line would be of this form, and that is, as you can see, that is quadratic in the coordinate and quadratic in the momentum. But our goal is to express this Hamiltonian in a more useful form. We want it to be in the form of a simple harmonic oscillator Hamiltonian. So therefore what we do next is we write the magnetic flux as in terms of plane waves. Plane waves are the normal modes of the system, and then we applied appropriate boundary condition. The periodic boundary condition is what we have taken, and the reason being is that that infinite transmission line is translationally invariant. Whether you go towards right or left in the transmission line, it doesn't matter. So we can imagine the transmission line to be some kind of a ring having, say, circumference W, and we divide this ring into a number of cells, each cell having cell size A, and we at a particular point x in the transmission line we can find out all the physical parameters. So say x is x, if we choose, then x is equal to n into a. N is an integer, and the boundary condition wise, as we discussed, this is actually result in that the wave number gets discretized, and kn is equal to 2 pi by w into an integer. N is an integer, and then answers we take it in this form, where it is superposition of lot of plane waves, and ak is the amplitude, and k lies between minus pi by a to plus pi by a. And because of the translational invariance, we find that it is easy to see that ak is equal to minus ak minus a minus k, and omega k is equal to omega minus k. And then we put this expression of this magnetic flux as well as this momentum in this Hamiltonian, and then we can there will be tedious calculations are there, but straightforward calculation we did not do that, but it can be done in the as it is done in the problem solving session. So you see that when you square Pn square, then you get this kind of a term here, but and you have to sum over k, 2 k's, one k over and k dash, and because the Hamiltonian, you see already it is summed over n, so there are effectively three sums are there, but this can be simplified further because of this orthogonality condition. So this orthogonality condition we discussed, and because of this orthogonality condition, the Hamiltonian is only over only one sum, that is sum over k. So there will be various terms. One of the terms in the Hamiltonian is of this type, but this term, as we discussed, is not wanted because it is a bilinear combination of these annihilation operators, and we don't want that our Hamiltonian should have this term, because ultimately we want our Hamiltonian to have ak dagger ak plus half kind of form is what is we want. So therefore this term we can cancel out if we take if we can make this term inside this curly bracket to be 0, and that can be done if we take omega k like this, and omega k is basically the frequency of the kth mode, and this dispersion relation, and in fact this is the dispersion relation for a plane wave propagating on the transmission line. And then we discussed this dispersion relation, and we found that when k is near equal to 0, then this dispersion plot or curve is nearly linear. And as we go to the continuum domain, you see as a tends to 0, this pi by a it's go in the outward direction in this side, and similarly this goes that side. So that actually means that the cutoff frequency for the continuum case, this actually the wave number would tend to 0. Okay, and this velocity on the transmission line would be simply given by this expression, where v would be square root of 1 by square root of LC. L is the inductance per unit length, and C is the capacitance per unit length. Then we had another term in the Hamiltonian. Now this term is the required one. We have the desired form here, and putting the dispersion relation that we derived or taken. So based on this equation, this Hamiltonian can further be simplified, so this can be written in this form. Now choosing ak in this form, we can write our Hamiltonian in a simple harmonic oscillator Hamiltonian form, which physically means that now our transmission line is nothing but a collection of independent simple harmonic oscillators. And we then have this magnetic flux as well as this potential also, or the voltage we can work out very easily as we discussed in the last class. Then we went on to discuss the quantization of transmission line resonator. A transmission line resonator can be obtained from the infinite transmission line simply by cutting the infinite transmission line at 2 points. So then we will have a transmission line resonator. But now in the case of transmission line resonator, obviously we cannot use plane propagating waves as our modes, so we have to take standing waves as we discussed, and these modes would be combination of either it would be sine function or cosine function depending on what we are taking n. For n is equal to 1, 3, 5, we have a sine. The shape of the mode would be sine function. For n is equal to 2, 4, 6, 8, like that. So you will have the shape of the function would be cosine. And then we also have this orthogonality condition. Using all these things and taking our coordinate like this and the momentum like this, now we are actually taking the continuum model. And if we put everything in this Hamiltonian, then we finally obtain again our Hamiltonian can be for the transmission line resonator can be written as a collection of independent harmonic oscillators. While doing this, we have taken our constant an to be like this, and the dispersion relation is this. And now from this thing we also discussed that how we can get the voltage in the transmission line resonator, which is a very, very important quantity. So this is what now we are going to discuss, because now the question is how to couple this fluctuating voltage V of X to the Cooper pair box. We know the Hamiltonian for the Cooper pair box and we know how an external electric field could be applied to tune the Cooper pair box. This external electric field is proportional to the fluctuating voltage V of X. This is in fact analogous to the fact that when you put a real atom in an external electric field where the interaction is say given by, this is I'm talking about a real atomic system where you put the atom in the external electric field, then this interaction term is given by this one, this expression where mu is this is the atomic dipole moment and ext, this is the external electric field. So analogous thing is also here, as I am now going to discuss. If you remember, our Cooper pair box has this charging energy term, we had q square by c, right? But then we have this q, and then to take the external field into account, then we put this gate charge there. And now because of quantum fluctuation, this gate charge is has some extra contribution, say delta qj. Okay, this is the quantum fluctuation, and then this is the charging energy term, q square by twice c. And in fact we can write this extra fluctuating charge as Cg into the fluctuating voltage. Cg is the gate capacitance, which depends on the geometry, and it depends particularly where we put the Cooper pair box in the transmission line resonator. So this is basically a geometrical quantity, and it takes actually details of many things, but in particular it is important where we are putting the Cooper pair box in the transmission line. Now expanding this Hamiltonian, just taking only the cross terms, because cross terms are only responsible for interaction. So if we take only the cross term, it is easy to see that I can write my interaction Hamiltonian in this form. If you expand it, you will see you will get a term like this: 1 by c q minus qz into delta qz. Okay, and this I can then use this expression, then I will have minus cz by c q by q minus qz into the voltage. That's how I can couple my Cooper pair box with the voltage. Now if we focus only on the single field mode, only one single mode rather than many modes, as you see we have this. So if we just focus on one single mode, then we need not have to deal with the summation, just one mode. Then I can write my this interaction Hamiltonian in this form: minus cz by c omega n a n phi n, that is the shape of the mode, and then I have a n plus a n dagger, and I have q minus qz. I just simply put the expression of vx, okay, in here, and that's what I get. Now I can exploit the fact that I can write my charge operator in terms of the number operator, as we discussed in the, I think, lecture 12 earlier. So I can write it as twice QE into n minus nz. N is the number operator. Now let us concentrate only on the ground state and the first excited state. Alright, so take the charge degeneracy point at say nz is equal to half, and our Cooper pair box would then be a two-state system, and this is actually this will enable us to express the Cooper pair box or this particular term in terms of Pauli matrices, because now it's a two-state system. As discussed in lecture 12, we saw that in lecture 12 we discussed that at nz is equal to a half, the ground state of the Cooper pair box is a symmetric combination of, we discuss it there, n is equal to 0 and n is equal to 1, and the excited state is a antisymmetric combination of n is equal to 0 and n is equal to 1. So this, if we take this ground state and the excited state as our basis state, okay, as our basis, what we can do now, we can express this operator n minus nz, we can write it in this form. So let me just quickly give you, we can write it as z n minus nz. You just have to expand it, z okay, kz bra z plus, so all these, there will be 4 terms. So very straightforwardly you can do the calculation here, and then we have other 2 terms will be z, say n minus nz, e, here it will be ze, and we have e n minus nz, z, e, z. Okay, this you can do. If you have forgotten, let me just quickly remind you. Suppose you have any operator a, I can always write it, I can I can sandwich it in this form, right? I can always sandwich a between the basis state ij, and then I just sum it. So this is what I have used while writing this expression here. Now with nz is equal to half, it is straightforward to show that n minus nz is equal to minus half ez plus ze. So this actually tells you, this operator tells you that you can go from ground state to the excited state, or from the excited state to ground state. So obviously this is our Pauli operator sigma x. So using this form, we can now write our interaction part of the Hamiltonian simply by this. So let me write it. It would be cz by c omega n an phi n of x an plus an dagger twice qe. Then in place of this one, I have this minus get cancelled out because I had here, this is minus, so therefore I will have a half sigma x. So finally what I can do, I can write my, this whole expression I can write it as h cross sigma sigma x cross z sigma x an plus an dagger, where I have put this constant s cross z includes this particular term, which is a constant cz by c omega n an phi n of x and qe. All right, so finally this is an important expression that we obtain, that is h cross z sigma x an plus an dagger. So this term Hamiltonian basically tells us how the two-level system or the artificial atom is now getting coupled to the transmission line resonator. You should note that h cross z has the dimension of energy and z is in frequency units. Z is known as the coupling parameter or coupling coefficient, and it gives us the coupling strength between the transmission line resonator and the artificial atom. And in a typical experiment, z is on the order of, it is in frequency unit, and so it would be in the order of megahertz, and one can actually have z up to or more than 100 megahertz. So we can have a very strong coupling between the artificial atom and the microwave field, depending on how we design the transmission line or the whole system. By the way, this model has a name, and this model is known as the so-called Jaynes Cummings model. and it's a popular model, and it is appears in many areas in physics, and we are specifically discussing it in the context of transmission line resonator and two-level artificial atom. Now our objective would be to solve this model and understand its physics. So Jaynes-Cummings model basically describe the interaction between a single field mode with an atom. For our case, the field mode is a single harmonic oscillator. So we have field and we have atom, and then we have this atom field interaction is there, and already I have written down the atom field interaction term. So in our case, the field is a one single mode we are considering, and that's a simple harmonic oscillator, and atom we are considering is a two-level system. So let us now write down the full Jaynes-Cummings Hamiltonian. The full Jaynes-Cummings Hamiltonian. So first of all, we have a field mode, so that we can write as a simple harmonic oscillator, A dagger A, then h cross omega, that is the frequency of the mode. I'm not writing plus half here because that's just a constant. And then the atom, we are going to model it as a two-level system, so we have this atomic transition frequency omega atom, and let me just write it as say sigma z by 2. Thereby I mean that my atomic this transition frequency is omega atom. In fact, if I just specifically talk about the atomic part of the Hamiltonian, then it would look like this h cross omega atom here by 2 and minus h cross omega atom by 2, because you know that sigma z is equal to 1 0 0 minus 1. And finally we have this atom field interaction term is there, and that we have already known, h cross z sigma x a plus a dagger. So this is what is the full Hamiltonian for the Jaynes-Cummings model. And the underlying physics described by the Jaynes-Cummings model is easy to understand. The first term in the JC Hamiltonian represents the field mode energy. The second term is about the energy of the two-level atom, while the third term represents the interaction between the atom and the field mode. And in our case, we have a situation like this, where we have our transmission line resonator, and in the transmission line resonator, say we have a field mode like this, and this field mode is interacting with the Cooper pair box or any artificial two-level system. And the coupling between this Cooper pair box and the field mode, microwave field mode, depends where we are putting our Cooper pair box on the transmission line, and the strength of this coupling parameter or its frequency z depends where Cooper pair box or two-level system is put on the transmission line, so it completely is dependent on the geometry. Okay, now we'll discuss the solution of this Jaynes-Cummings model, and for our convenience, let me take the ground state of our two-level system to be at 0, and excited energy state would have energy h cross omega atom, where omega atom is the transition frequency between the ground state and the excited state. Earlier we had situation like this, where the ground state energy was taken to be h minus h cross omega atom by 2, and the excited state had energy h cross omega atom by 2, and the transition frequency, of course, still it's omega atom. So nothing is actually getting changed, only I'm just shifting my energies, and that has actually would turn out to be very convenient. Then I have to make a little bit of changes in the James Cummings Hamiltonian. Let me do that. So first term would remain the same in the James Cummings Hamiltonian, that is the H cross omega A dagger A, that is the field mode energy, and the atom energy would be of this form now, omega atom sigma Z. I will just put a plus 1 there, divided by 2, and then this interaction term remains the same, H cross Z sigma X A plus A dagger. Now you see that this guy sigma Z, when this is equal to plus 1, this refers to the fact that the atom is in the excited state, and you can immediately see that if I put sigma Z is equal to plus 1 here, then my energy of the excited state of the two-level atom would be simply H cross omega atom. And on the other hand, when I have sigma Z is equal to minus 1, then the atom is in the ground state. Okay. Now, surprisingly, this James Cummings model has no analytical solution. So JC model does not have I mean exact analytical solution. Exact analytical solution, though it is such a simple model, but we can still solve it approximately. It can be solved approximately under the so-called rotating wave approximation, RWA, and weak field limit, weak field condition, weak field limit. By weak field limit, I mean that it implies that Z, this coupling parameter Z, is very weak. In fact, that means that this last term, this coupling term, is now going to be considered as a kind of a perturbation. And also please note that when this parameter Z is equal to 0, that is, there is no coupling between the atom and the field, we cannot solve the James Cummings model, because in that case what we have is we are having simply the atom, which is a two-state system, and we are having this field mode, which is a harmonic oscillator, as we know, and this harmonic oscillator has infinite energy levels and all of them are equally spaced, right? And virtually nothing happens, so we are not going to have any solution in the model. Okay, nothing useful we can get out of this. So now let us draw the energy level diagram for the combined atom field system. And in this process we are going to take the number of photons. So what we are going to do, energy level diagram, we are going to draw energy level diagram for atom field system, and while doing that we are going to take the number of photons inside the field mode with the atom to be either in the excited state or in the ground state. Firstly, for simplicity, let me consider the easiest case, that is when the coupling is 0 between the atom and the field. We can view the atom as a spin half system, as it has only two energy level. let us say we have the atom is in the ground state. Okay, atom is in the ground state. Say, let me represent it by the down here, down spin. It is in the ground state and there is no photon in the field mode, zero photon in the field mode. So clearly this is the ground state of the combined system, combined atom and field. So this represents the ground state energy of the system. Now we can put one photon into the field, the atom still being in the, say, ground state, and then we have this one photon in the field mode. So the energy would be, then energy of the system would enhance by h cross omega, because h cross omega is the energy of the field. And then if we put another photon, then energy would be enhanced further. With respect to the ground state, the energy would be twice h cross omega. Now atom is in the ground state and there are two photons in the field mode, and so on. We can go on and on in the upper direction. So this is in what we have is the energy. On the other hand, we can have a situation where the atom is in the, say, excited state. Atom is in the excited state and there is no photon in the field mode. Then because the atom has energy h cross omega atom, so this energy level is shifted from the ground state energy of the combined system by h cross omega atom. And as you see, this particular level, let me put this color here, this particular level and this level, it has some energy difference. That energy difference is, or frequency difference is, as you can see from the diagram, that would be omega atom minus omega, and this has a, this difference in frequency has a name. It's called the detuning parameter and it's very important. So delta we are going to denote is as the so-called detuning parameter. Okay, so this is detuning parameter, and when the system is in resonance, so in that case omega atom is equal to omega. Now if we put another photon in the field mode, now if we put a photon in the field mode, then our energy state would be this, combined system would have energy this. So this would be, because we have put field mode, so it would be h cross omega, and so this way you can go on draw the other energy levels. Okay, now let us switch on the, here we discuss the case when the coupling between the field and the atom is 0. Now let us switch on the coupling, switch on the coupling. All right, so that means when z is not equal to 0, and of course as I said that we are going to consider the coupling to be very, very weak, and then we can exploit the fact that the energy levels which are resonant, in resonance, or they are nearly resonant. For example, okay, for example, if you just look at these two energy levels, they are nearly resonant, lying nearby. These energy levels are far more important than the off resonant transitions or energy levels. For example, we can neglect the transition between say this energy level and this energy level, or say this energy level and say this energy levels. Hope you are getting the idea. So we can just neglect interaction between these energy levels, and in that case basically we are neglecting all the off resonant transitions, and this is the so-called rotating wave approximation. So we are going to neglect all off resonant interactions, as will be clear. That is possible only if we have this coupling parameter z is very weak. Okay, then we can neglect all the other off resonant interaction, and now under the so-called RWA, under this is called RWA, under RWA we can write this term, last term in the James Cummings Hamiltonian, sigma x a dagger, we can write in this form. Sigma x can be written as sigma plus into sigma minus. Let me explain that. A plus a dagger. You see, sigma x is equal to 0 1 1 0. This we can write as 0 1 0 0 plus 0 0 1 0. Now if you can recall from your earlier class that this part is nothing but the atomic raising operator sigma plus, and this one is atomic lowering operator sigma minus. Okay, now under RWA, or the so-called rotating wave approximation, I can write, if I expand this whole term, I will get 4 terms, but out of these 4 terms, because of RWA, I can just keep only 2 terms, and those would be sigma plus A and sigma minus A dagger. Here we are discarding terms like, we are discarding 2 terms, those are sigma plus A dagger and sigma minus A. This is physically reasonable because, for example, we know that this sigma plus A, this whole thing implies that because this is sigma plus is atomic raising operator, so it means that atom is raised from or excited from the ground state to the excited state, and then in the process a photon is getting absorbed. And we know that this is indeed true, and this is physically what happens. Similarly, in this case, you see sigma minus A dagger, it means atom is now getting lowered, atom is transiting from excited state, from, let me just write like this, from excited state to the ground state, and in the process a photon is getting created, a photon is emitted, right? A creation of photon is happening, a microwave photon happens in the case of our system that we are considering, a transmission line resonator interacting with a Cooper pair box. So this is very reasonable. On the other hand, you see these two processes, say sigma plus and A plus, this means that what is happening, that when the atom is getting excited, a photon is also getting created. These are very unlikely, very probability of occurrence of these two events, say this one and another one is this sigma minus A, which means that when the atom is now getting de-excited from the excited state to the ground state, a photon is getting absorbed. That is not the case, right? These are two unlikely events, so therefore we can safely we can ignore these two terms. I hope it should be now clear to all of you. So in that case, then we have this so-called RWA Hamiltonian, the James Cummings Hamiltonian under RWA. We can now write it as H cross omega A dagger A plus H cross omega atom. We have it as sigma Z plus 1 by 2, and then we have H cross Z. I have sigma plus A plus sigma minus A dagger. So this is what we have and we are going to discuss it now. Let us switch on the coupling parameter, that is when Z is not equal to 0, and see how the level scheme looks like. We have Z non-zero and this coupling parameter is weak, and because of that, as per the rotating wave approximation, only the neighboring energy levels, for example this energy level and this energy level, are connected to each other. Similarly, this energy level and these energy levels are connected, and similarly for all higher energy levels in the ladder. Or we can say simply that the state where the atom is in the ground state and there are n number of photons in the field mode, and atom in the excited state and there is one less photon in the field mode, they are connected to each other. And the matrix element in the James-Cummings Hamiltonian which connect these two energy levels or these two states can be worked out very easily. So let me work that out. So we have this state, atom in the ground state and photons in the field mode, and the atom in the excited state and one less photon in the field mode, and this is connected via, basically coupled via this term in the JC Hamiltonian, H cross Z sigma A dagger plus sigma plus A, right? So this is what we have to work out now. Actually it will turn out that this would be simply H cross Z square root of n. Let me show how it can be worked out very easily. Let us see the action of this operator on the state. Say sigma A dagger, this one. So this atomic, now this is the lowering operator, sigma minus. Atomic lowering operator would act on this atomic state, and A dagger is going to act on this photon state, field state, and we know that this is simply n plus 1 into actually it is square root of n plus 1 and n plus 1 ket here. Now this is the atomic lowering operator, it is acting on the ground state, so it cannot lower it further, so therefore this is going to give us 0. So overall we are going to get 0 because of this. Let us look at the other term where we have sigma plus A, this one, acting on this state. Sigma plus atomic raising operator is acting on the ground state of the atom, and then annihilation operator is acting on the field mode. And you know that when it is acting on the field mode, we are going to get simply square root of n minus 1. And on the other hand, this, because of this action, this ground state is going to be raised to the excited state. So therefore we'll simply have square root of n atom in the excited state, and field is having n minus 1 number of photons. So let me put this term here. So what you are going to get because of that, you will have this up state n minus 1, and I have h cross z square root of n, and I have, this is my state. Now this is just a number, and these two states are the same state, so they are normalized, and because of normalization we have simply h cross z root n. Okay, so this is how these two energy states or the two are connected to each other when there is very weak coupling between the states. Well, let us find the matrix form of the James-Cummings Hamiltonian in the rotating wave approximation. So our James-Cummings Hamiltonian, let me rewrite again. It is h cross omega A dagger A plus h cross omega atom sigma z plus 1 by 2 plus h cross z. I have sigma A dagger plus sigma plus A, right? So this is our James Cumming Hamiltonian in the RWA. My intention now here is to work out the matrix form of this Hamiltonian, and for that let me choose my basis state as this. These are my basis states. Basis states are simple, and this is atom in the ground state, and number of photons in the field mode, atom in the excited state, one less photon in the field mode. Okay, taking this as my basis states, in fact let me write it in a shorthand notation. Let me denote it by this kth alpha, and let me denote this state by kth beta. So the Hamiltonian, then just recall that any arbitrary Hamiltonian I can always write in this form. I can sandwich this Hamiltonian between these states because of the completeness condition, and I have to take sum over all this here. So therefore this JC Hamiltonian, now I can write it as, because I have only these two basis states, alpha beta, right? So I can write it as alpha H alpha alpha alpha, and I have beta H, I have, okay, let me write it properly. I have beta H beta beta beta, and I have alpha H beta alpha beta plus beta H alpha beta alpha. So this, let us work out all these elements. Already actually we have worked out this element beta H alpha, which I can actually denote it as H beta alpha, and beta we have taken as up state of the atom, and n minus 1, that's the field photons, H down state of the atom, and this is n, right? That's how I have taken my alpha and beta. So this already we have worked out, and this is simply h cross z square root of n. Similarly, you can work out h alpha beta, that means alpha h beta. This would be also equal to h cross z n, and please try to find out what is h alpha alpha, that is alpha h alpha, that would be equal to h cross omega n. You can very easily work it out, and h beta beta, that is beta h beta, that would be h cross omega n minus 1 plus h cross omega atom. This actually I can write it as h cross omega n plus h cross omega atom minus omega, and this, you know, this is the detuning parameter, so therefore I can write it as h cross omega n plus h cross delta, right? So I have all the elements in the Hamiltonian, so I can write my James Cumming Hamiltonian in the matrix form now. So we have h alpha alpha, h alpha beta, h beta alpha, h beta beta. So as I have worked out all the elements, so let me just write it down. That would be h cross omega n, h cross z, these are the coupling term, h cross z root n, and I have h cross omega n plus h cross delta, where delta is equal to omega atom minus omega. Now let us find out the eigenvalues of this James Cumming Hamiltonian in the RWA. That can be done very easily. Let me show you. This Hamiltonian I can write in a simpler, let me separate it out in a number of terms. Let me write. To find out the eigenvalues, I need to diagonalize it, and I can do it this way. I can write it as h cross omega n 1 0 0 1, then I would be left out with 0 h cross z square root n, h cross z square root n, then I have here h cross delta. It's easy to see, right? And then I can further write this guy as S cross omega n 1001, and this I can write this further as H cross delta by 2 1001, and I have minus H cross delta by 2 here, and here I write H cross delta by 2. So as you can see, I have, if I take this term and take this term, I will have the diagonal elements there, and this one would be simple, that would be H cross z root n and H cross z root n. The good thing is that this particular part in the Hamiltonian is already diagonalized, this is also diagonalized. Now I have to just diagonalize this part of the Hamiltonian. So let us do that, but actually we need not have to do that, because already from module 1 when we discussed the two-level atom, you just recall that when we wrote down this Hamiltonian for the two-level atom, epsilon z minus epsilon z, epsilon x plus I epsilon y, epsilon x minus I epsilon y, there we saw that the eigenvalues of this Hamiltonian we worked out, and that was mod epsilon, that is equal to plus minus square root of epsilon x square plus epsilon y square plus epsilon z square. So let us use this result directly for this particular part in the Hamiltonian. That is, okay, let me write it separately here, h cross minus s cross del by 2 s cross z root n, h cross z root n, and h cross del by 2. So the eigenvalues is lambda, let me denote it by lambda. So I have plus minus h cross del by, just look at here, h cross del by 2 whole square plus h cross z root n. So I know the eigenvalues of this Hamiltonian, I know the eigenvalues of this Hamiltonian, so therefore the overall, so the overall we have the eigenvalues of the Hamiltonian, James Cummings Hamiltonian under RWA is this, E plus minus is equal to h cross omega n plus h cross delta by 2 plus minus h cross z square n plus del by 2 whole square. Or if you are more interested, or simply we have two energy eigenvalue, E plus and E minus. E plus refers to h cross omega n plus h cross del by 2 plus h cross z square n plus del by 2 whole square, and E minus is h cross omega n plus h cross del by 2 minus h cross z square n plus del by 2 whole square, right? Now let us consider the resonant case. It is simple to understand. In the resonant case, delta detuning parameter is equal to 0, so therefore we will have these energy levels as E plus E minus would be equal to h cross omega n, you will have plus h cross z square root of n, and here you will have h cross omega n minus h cross z square root of n. Okay, that's why you see, that means the energy level is basically getting splitted into two parts. Let us understand it from the energy level scheme or energy level diagram for this system. We have the atom in the ground state, and there are no, this is what photons in the field mode, so this is our ground state. Then we have atom in the ground state, 1 photon in the field mode, atom in the ground state, 2 photons in the field mode. Right, now because it is resonant, so in the other case we have here atom in the, here I am talking about when there is no coupling, the atom in the excited state and there is no photon in the field mode. These are now, horizontally lying because delta is equal to 0. So the atom in the excited state, 1 photon in the field mode, and so on. You can go on. Now when the coupling is switched on, this is the same energy level, they have the same energy. This is getting splitted up into two parts, one is E plus and another one is E minus. So if you just look at this particular these two states, then you see how they are connected. This atom in the ground state, one photon in the field mode, and atom in the excited state, no photon in the field mode, and this interaction term H cross Z. I just have to write, okay, I just can write it as yeah, sigma A dagger plus sigma sigma plus A, right? This would be if you just look at from here where we have worked out the matrix element. Okay, this expression you see, n is this one, right? So therefore from here I can, because n is equal to 1 I have to put, so this would be simply H cross Z. Okay, and if you look at now these states E plus and E minus, so therefore I hope you are getting it. So this is my E plus and this is my E minus. So E plus, let me use this, E plus is H cross omega plus H cross Z, and E minus, this is H cross omega minus H cross Z. So therefore the splitting in the energy level is simply twice H cross Z. Similarly, you can show that these energy states are getting splitted into two parts, E plus and E minus, their corresponding energies. So, and this splitting would be, if you work it out, you will get it as 2 into square root of 2 H cross Z.
Let me stop for today. In today's class, we saw how quantization of the transmission line resonator leads to the so-called Jaynes-Cummings model, and we have also learned that there is no analytical solution to the Jaynes-Cummings model. However, we can solve this problem, the Jaynes-Cummings model Hamiltonian, we can solve under the so-called rotating wave approximation. We have written down the matrix form of the Jaynes-Cummings model under the rotating wave approximation. In the next class, we will continue our discussion on the Jaynes-Cummings model, and we will particularly discuss the dynamics associated with the Jaynes-Cummings model along with some other features. So see you in the next class. Thank you.